This meeting is being recorded.
In the last video from chapter 17, we took a look at sample exercise 9. And if you recall, we worked through parts 1 through 3. So before we added any sodium hydroxide, then we solved for pH. And we found that to be 4.56 at this point here. So we had 2.52 increased to 4.56, and then we find at point 3, our pH equals our pKa. This, we call this our half equivalence point. Let's see what happens in part 4. So notice that we're adding 20 milliliters and 0.5 molar sodium hydroxide to 20 milliliters and 0.5 molar acetic acid. So hopefully you notice that they're the same concentration, the same volume, so we're going to end up with the same amount of moles. So that's what we can see up here, that we have 0.01 moles of acid, that's remained the same, and now we have 0.01 moles of base also. So let's see what happens if we try to plug those values into our ACE table here. So our weak acid, all of that gets consumed with our strong base. So we have 0 weak acid, 0 strong base. And then we started with no weak base. We've added the 0.01 molar strong base. So we end up with only 0.01 for our weak base here. If we try to plug this in down here to the Henderson-Hasselbalch equation, we would see that pH equals our pK of 4.7 fluor, plus the log of our base over our acid. So this won't work because we can't have 0 in the denominator. So instead, we're going to use a different process. We're going to create a weak base ice table. So we have our reaction here. So our weak base is going to be our acetate. We add that with water. We get our product, acetic acid, and then we get hydroxide. All right, so let's look at our initial terms here. So we had we have to find what our initial concentration is of our acetate. So in order to do that, we're going to take our weak base, right? We're going to find our weak base molar concentration. We know that we have 0.01 moles from our table up here. We're going to divide by our total volume. So at this point, that's going to be 0.04 liters. So this gives us a 0.25 molar initial concentration here. So that's how we found this value here. So we have 0.25, nothing here. And then to start, we have none of these. So our change is going to be minus x. So we'll fill this in, 0.25 minus x. This is plus x, so x plus x, also x here. So now we have some variables that we can plug into a KB expression, and I've already solved for KB up above here. This 5.6 times 10 to the negative 10, that was derived from KW divided by our KA value given previously in the problem. So now let's look at our KB expression here. We're going to have x squared, so products over reactant. Recall that this x is small. It's negligible because our KB value is very small in this case here. So we're going to set this equal to our 5.6 times 10 to the negative 10. Now we're going to have to rearrange this and solve for x. So I'm going to multiply over here by 0.25. If I multiply on this side, that will cancel out. And then I just need to take the square root on both sides to solve for my x. So my x value will turn out to be approximately 1.2. We'll squeeze it in over here. X is going to be equal to 1.2 times 10 to the negative 5. And again, this is my hydroxide ion concentration. So I can use that to solve for POH. If I take the negative log of 1.2 to the -5, I'm going to get a pOH value of 4.93. So now to find pH at this point, I can simply do 14 minus 4.93, and that gives me a pH of 9.07. So this is a basic equivalent point. And that makes sense with a weak acid, strong base combination. So let's take a look at the conditions for part 5 here. Now we know we have the same amount of acid. Moles of A is always going to be 0.01. Let's jump back up here. Now we've added 21 milliliters of our 0.5 molar sodium hydroxide. So let's look at how those calculations will look here for moles of base. So we have 0.021 liters times 0.5 molar. Now we're going to get 0.0105 moles of base. So we're going to use this in our ice table. So we have our acetic acid plus our sodium hydroxide. So our acetic acid is always 0.01. All of that's going to get used up. This is our limiting reactant, or reagent, we can call it, because there's more moles of base present. So we're going to start with 0.0105 here, subtract all of our acid that reacts, 0.0100. So we get a remainder of 0.0005 moles of hydroxide here. And then we have to write our product side here. So now we're going to have our sodium acetate over here. And we'll start with nothing. We'll add 0.01, just like we subtracted it from over here. So now that's what we have left over here. So in this case, we're concerned with just the excess base. So we're going to take this value here. We're going to solve for our hydroxide ion concentration. So we have 0.0005 moles of base. That's right, 3 zeros in a row. We're going to divide by our total volume. Now it was 20 plus 21 milliliters. So we're actually going to have 41 milliliters total. So 0.041 liters. We'll divide moles by liters. We get a concentration of 0.012 molar hydroxide. There's 2 last steps for this problem here. First, we're going to solve for pOH, and that's going to be the negative log of our hydroxide ion concentration. For that, we get 1.92. And then last, we'll solve for pH at this point. That's going to be 14 minus that 1.92. We get our highest pH found so far, 12.08. So let's go back to our table, or our initial information given here, and let's look at how our pH has increased. We went from 2.52 to 12.08 following these 5 points of addition. And the last thing that I wanted to note in this video is this graph here from your worksheet, where we have various pHs shown along the y-axis, and you can see different equivalence points indicated over here by these dots. And notice as you get a weaker and weaker weak acid, so the weakest up here, there's really a very small change between the equivalence point here as you increase from acidic to basic. So notice with strong acids, there's a much more pronounced difference in pH as you hit that equivalence point.